All right, I'm Martin McClure, and many of you know me, some of you don't. I've been using Smalltalk a very long time. Yesterday, Dave West mentioned early days in Minneapolis, and that brought back some memories. Dave West can legitimately claim most of the Minneapolis area Smalltalk developers, but not necessarily all of them. In 1985, I started a Smalltalk user group in Minneapolis. The first meeting was held in my house. There were 5 of us there. None of us had ever run Smalltalk. It's possibly the only Smalltalk user group with that particular distinction. I had ordered the Apta Smalltalk from Apple, which came on 7 floppy disks for the baby Macintosh. Would run in 512K, and it hadn't quite arrived yet. It arrived a couple of days after the meeting. I was hoping it would arrive before the meeting so we could actually run Smalltalk at the meeting, but no. So we just talked about it. It arrived a few days later, so at the next month's meeting, I was the expert because I had had 3 whole weeks to run Smalltalk with no guidance from anybody except the Blue Book and the image itself, which is a pretty good guide. Anyway, these days I work on the GemStone line of products at GemTalk Systems. You'll be hearing more about that in this talk. And this talk is about threads, which is a big subject. So I'm just going to talk about a few of the little corners that I've run into and some things that I've had to do as a result, which are probably things that you shouldn't do. So I'm going to use the word thread. The class in Smalltalk is named process. That was back in the 70s when Smalltalk was being designed. Process and thread weren't defined as clearly as they are now. I may slip up and use the word process sometimes, but I'm going to try to use thread. I will mean the same thing either way. Usually the way it's currently defined, that if you use the word thread, you mean that you have shared state and between the threads. The sharing state is the hard part of concurrency, because that's where you get your race conditions. That's where you get all sorts of other problems trying to prevent race conditions. Some languages isolate the state by default. Languages like E, Erlang, that sort of thing. You have specific things to pass messages between the threads, but you can't actually directly interact with the threads. And the thing we just saw with Taskit, which has the futures, is one of the mechanisms for doing that. And it's great to have that in Smalltalk. The problem is that you can accidentally share every other object in your image without meaning to, and then you're going to have problems. So you have to limit the sharing through extremely careful design. And actually, shared state threading is a terrible model. Don't ever use threads if you don't have to. But sometimes you have to. I have to. The reason I have to is this product that we have called GemBuilder for Smalltalk. And this is also known as GBS, which is how I refer to it throughout this talk. It's a special purpose distributed object system. It works between a VisualWorks or VA client to a GemStone server. It replicates objects, synchronizes the state between the client and server, passes remote messages, that sort of thing. This was first released in 1986. I've been working on it since 1996 for GemStone, and I've been the team leader of the team that develops this product since 2002. And it uses threads internally, and always has, at least ever since I've been working on it. And not only that, but this is a framework that is meant to be used to develop applications on top of. And those applications are allowed to be multi-threaded. So I can't predict how threads are going to be used. So I have to be very defensive in how I program this to allow any possible use of threading to continue to work without error. There are VW and VA versions of GBS. All the examples I'm going to give today are from the VW version. So inside of GBS, we have a couple of core data structures that are mapping dictionaries. And these keep track of the identity of objects between the client and the server. So we have two of these, one that is keyed by the server's object identity and one that's keyed by the client object identity. And these dictionaries have to be shared between threads. I'm going to talk mostly today about the client map. This one is keyed by the client object. So it is effectively an identity dictionary of sorts. It's not subclassed from identity dictionary or anything, but that is its semantics. We have customers that use up to 2,000 keys, or 2 million keys, excuse me, at a time. Don't know of anybody who's using it more than that. But that would mean 2 million objects that are currently have their state replicated between the GemStone server, which can hold many more objects than that, and the client, which can also hold many more objects than that. But these are the ones for which we're tracking the identity so that they're logically the same object. When we're in the act of replicating objects from the client, or from the server to the client, we can be doing about 100,000 updates per second, new things added to this mapping dictionary. And we can be doing at least that many lookups, maybe several times that many lookups. So maybe up to getting up towards a million lookups a second. So the structure of this thing, we've got a key. Keys are weakly held because we don't want to keep the client object alive just by having it in the mapping dictionary. It's up to the client application to release it when it's ready. The value, which is held strongly, is an object that keeps track of things like the server identity, the server object ID, the session that it belongs to, whether or not the state is currently synchronized or whether it needs synchronizing, that sort of thing. So this is going to be the structure that I'm going to talk about is specific to 32-bit VisualWorks. The 64-bit VisualWorks has a rather different structure. The reason for that is that 32-bit VisualWorks only has 16K identity hash values, and it's identity keyed. So in 64-bit VisualWorks, there's 20 bits of identity hash. So I can just use one big linear probing table, like I talked about in last year's talk, to have up to my 2 million key value pairs. But in a 32-bit VisualWorks, I only have 16K cache values. So the structure that I use is to pre-allocate one bucket for each of the 16,383 possible hash values. And then I can just take the identity hash, look it up in the dictionary, and I'm right there at the bucket. 0 is not a value you will ever get out of VisualWorks for an identity hash. So that works out pretty well, since we don't have the array access of 0. The structure of a bucket is we have a bucket object which has a reference to a weak array that holds the keys, and we have the arrays at the same, within the bucket at the same indexed instance variables that have the corresponding values at the same indexes. We have free slots. Those are linked together in a linked list, so we know where to find all the free slots. The keys and values never move within the bucket. So the question for the purpose of this talk is, how do we safely share this structure between threads? Well, the obvious thing is to use semaphores. Semaphores are a synchronization primitive that comes with Smalltalk. Back in the 70s when Smalltalk was being designed, semaphores were the hottest new thing on the block. There were a number of less useful primitives before that for synchronization. But I have to think about, how's that going to perform if I mediate every access or modification to this data structure with a semaphore? So I'm going to digress into a little bit of a rant about performance. So I happened to find this quote just a few days ago. I'm not sure I agree that it's the root of all evil, but it's the root of a lot of evil. So I'm going to be talking about some things that you probably shouldn't do, and you probably don't need to do. And we'll talk about exactly that. But the things I really like to optimize for are simplicity and clarity. And then if the system runs fast enough, that's great. Sometimes they don't, and you need to make things a little more complicated when it actually buys you something. So I have to pay attention to performance, and the reason for that is we have some customers that use this, not for GUI applications where you're talking about human time, but for internal applications, server-side operations, where you were talking about computer time and things have to be very tight. So we have one customer in particular who had a particularly tight time requirement for a certain set of objects being transferred from the server to a VisualWorks client. And they needed to set this particular tree of objects. They had to get there in 5 milliseconds. And about a decade ago, they were switching from the 32-bit GemStone product to the 64-bit GemStone product, which doubles the size of the object identifiers, almost doubles the amount of data that we have to handle in GBS in order to process the buffers over the wire that these come in on. And the time went from 5 milliseconds to 9 milliseconds in their tests, and this was not acceptable. So I spent a few weeks at the customer's location, shaving performance out of GBS almost any way I could, and we got it down to 3 milliseconds. And you know what happened then, right? 3 milliseconds is now the benchmark. We can't be slower than 3 milliseconds. So in light of that, I have to look at what using semaphores would do to my performance. So let's run some tests and see how expensive semaphores are. So if we execute an empty block a million times, what's the overhead of that kind of test? Well, it turns out that it's 3 to 4 nanoseconds per iteration. All of the things I'm going to show you are results of 1 million iterations, so I'm just going to show it like this, empty block, 3 to 4 nanoseconds. Okay, so let's do some more interesting blocks. How about this one? What does it cost to do a semaphore critical on an empty block in VisualWorks on one particular machine I happen to have at work? It's about 70 nanoseconds. Well, is that slow? Is that fast? We don't know without something to relate it to. So, well, let's compare it to what it costs to do a dictionary lookup. So this is the lookup method of, this is effectively @ for this particular specialized dictionary. How long does that take? Well, it takes about 40 nanoseconds to do a lookup in this dictionary. So clearly I'm not actually using a semaphore, since a semaphore alone takes 70 nanoseconds. And we can test that by wrapping my lookup in a semaphore critical, and 70 plus 40 is, don't ask me, I have no idea where the extra 20 nanoseconds comes from. Nevertheless, this is what I tested. So is 130 nanoseconds too slow for a lookup? Well, if you're doing 1,000 lookups a second, probably not. It's probably just fine. If you're doing 1 million lookups a second, and I'm approaching 1 million lookups a second, then 130 nanoseconds, or 70 or 90 nanoseconds per lookup overhead is something that I don't really want to look at. So once again, if you're only doing this 1,000 times a second, don't do what I do, because that would be premature optimization. But here's what I do. So for modifying the dictionary, I do use a semaphore, but I use it on batches. So the updates come in batches. I acquire a semaphore once, do a whole bunch of updates, release the semaphore. So I only incur this overhead one time. This complicates the logic, and I have to be a lot more rigid in developing the code, because this breaks the encapsulation, in that the protection of the dictionary is not in the dictionary. It's external to that in the way the dictionary is used. But that does help a fair amount in the performance of this collection. For lookup, I don't get semaphores at all. Anybody can look something up in this thing at any time. But how is that safe? What if it's in the middle of being updated? What if it's in an inconsistent state? So we have to give a sane answer no matter what. So here is some of the code for doing the hash bucket lookup. So as we saw before, getting which hash bucket to use is just the identity hash of the key. Once you're in the cache, once you're in there, you just do a linear search for the key, which, the code for that didn't fit on the slide in a readable way. Then we say, well, if we didn't find it, we return nil. And if we did find it, then we get the value that corresponds to it. And then it's these last two lines that are additional work that I do to make sure that we're consistent, which is I then relook up the key. Now, we found the key up there. We know it's there. We know its position. So we say, well, what is it? Is it actually identical to the key that was there a minute ago or a couple of nanoseconds ago? And then if it is the same key, then we got the value. And if it's not, nil. Well, why nil? Well, keys are never moved in this dictionary. And usually, the usual way that keys get removed from this dictionary are through garbage collection. So nil is a legal answer, even if the key was removed during this search and then re-added. There was some point around this point in time when nil was the correct answer because it wasn't there. And if you're not synchronizing, any answer that was valid in roughly that time period is a valid answer. It does require these extra 2 lines of code. So you might ask, well, how much do those cost? Well, this was the code that produced the 40 nanosecond result. So it's included in that figure. Now about adding, how do we add things? Now this is semaphore protected, but we also kind of have to coordinate between the add and the remove. In particular, here, we find the free index within the bucket, and then we say, put the value in self, the bucket, and then add the key. And the order of those two things is critical, because we have to add the value before we add the key. Now, fortunately for this particular algorithm, Smalltalk is green-threaded, and therefore we know, unlike with native threads, that things that we observe happening in other threads we see the effect of those in the order that the other thread did them. This is not a guarantee that happens in native threads. But because we're single-threaded from the native point of view, we do have that guarantee. So if we go back and take a look here, I find the key first and get the value. I don't have to worry. If I added the key to the dictionary before I added the value, I might find the key between the adding thread might have been suspended between adding the key and the value, and then I'd find the key and give the wrong value for it. But if I add the value first, that won't happen. But when I was preparing this talk, I found, hey, look, there is a hole in that logic. Does anybody know what that is? There's theoretically a way to get the wrong value for a key out of this. So if you delete things, the way to get the wrong value for the key would be that if the key is there here, and then somewhere between there and here, that key is removed, another key is added to the same slot with its value. You get the value that belongs to the other key, and then you get suspended again, and that key is removed, and another key is added. And then you check to see if the key is there identically, and it is. and then you would actually give the wrong answer. Interestingly enough, in the 64-bit version of this structure, I account for this by having a deletion count that is maintained by the collection that we also check to see whether the deletion count is the same at the end of the method, at the end of the lookup and before, and if it isn't, we restart the lookup. This one is very unlikely to get hit because, as I said, keys are usually removed through garbage collection, and if they're removed through garbage collection, then it's impossible to add the identical key again. So, also, well, it won't be garbage collected because we actually are holding on to the key here. Nevertheless, there are a few cases where you do delete that, so I may actually go in and fix that. So let's go back to this method for a minute and get to what I really kind of wanted to talk about, which is there's something funny on this slide. And it's right about here. I am sending ensure to an empty block with an argument of a non-empty block. Why is that? So what we've got here is the update. We've got, various steps that we have to do. We have to increment the size, change the key, change the value. Once you start this, the collection is in an inconsistent state until you get down to the end. So what happened was that a number of years ago, we were reworking a lot of the lower level layers of GBS, and the login sequence exercises about 80% of the low level code in GBS, and so getting through the login sequence was taking weeks. And we'd get partway through the login sequence, and we'd hit a debugger, find the bug, close the debugger, and then the image would be all messed up because the state wouldn't be good. And I decided this was unacceptable for us and for our customers. And I decided that we should add a bunch of ensure and if curtailed blocks in the appropriate places so that no matter where you were in the sequence, if it got terminated, it would clean itself up. And I added a test for that, which is a rather abusive test that sits there logging in and logging out and logging in and logging out many times a second for about 30 seconds, and this process would get killed at random intervals. So, and then what we had was hung tests. The tests would hang on a blocked semaphore, a semaphore that no one was holding. Well, after a lot of research, we found that it was this. This is how semaphore critical is implemented in VisualWorks. So you wait on the semaphore, and then once the semaphore is released, you execute the block, but you have an ensure of self-signal. And what was happening is if the timing was just right, and we saw this multiple times, not every time by any means, but multiple times, was the execution would get into the ensure block and would be right here before this signal was sent, and the process would be terminated. And the semaphore would never get signaled. So we talked to Syncom about this, and they kind of agreed that this was a bug, and they eventually fixed it, which I don't think was simple. But the idea is that if an ensure block is running when you send to terminate to a process, then it ought to be allowed to complete. That ensure block ought to be allowed to complete unless it, signals an uncaught exception or something like that. So they did fix that, which solved our problem. This is a test. It'll be in the slides. You don't have to read it now. For seeing whether your favorite Smalltalk actually has this bug or not. VW no longer has the bug. Pharaoh does not have the bug. I'm afraid GemStone does. I reported this a couple of weeks ago. VA also has the bug, but test it on whatever you like. Basically makes a big window for catching that. So if you're in a critical section and your process gets terminated, how do you deal with that without leaving yourself in an inconsistent state? So we have this hash bucket add. Here I've got the empty block, the ensure, and I've got my entire critical section in an ensure block. And in VisualWorks, since about 7.6, when they fixed the bug, this works. All right, once I've started this, it will finish. I am proof against being sent terminate. All right. Well, okay, there's got to be other ways of dealing with that, right? Is this really the best way? So, well, there's semaphores. That's what we usually turn to. There's also a couple of messages that we might use. So, Semaphore, can it help us? Well, it can protect us against interference from other threads, but it's not generally designed to protect against being sent terminate. So we're already protecting the whole batch of updates against interference by other threads, but that doesn't protect against thread termination. And also, there's that 70 nanoseconds that I don't really want. Value uninterruptibly, this would actually protect against this sort of thing. Since termination does have to interrupt the thread, there's an interruption semaphore that is per thread that has to be obtained in order to get that. But using this might have some unintended consequences. Debugging also uses thread interruption, and it might make these threads hard to debug. So slightly bigger hammer than I wanted to use. Also, it uses a semaphore, so 87 nanoseconds. Okay, value unpreemptively. This would actually work. It's a really big hammer. It sets the priority of the process of the thread up to the maximum priority so that nobody can preempt it. So it will definitely get through the critical section. But that's a bigger hammer than I need. I don't need to prevent any other thread from preempting me. As long as I finish that critical section sometime, it's going to be okay. Anybody else that's going to try to modify this thing has to go through the semaphore I've already got. So I don't need that big a hammer. And then there's also, how much time does that take? 175 nanoseconds. Okay, so it's even slower. So, but how fast is that, the thing that I'm actually using? 15 nanoseconds. By far the fastest way to do this that I have found. So, a couple of final thoughts. So, from my experience of having to deal with threads in this product and in others for 20 years, number one, don't use threads, okay, unless you have to. If you do have to use threads, keep the state as separate as you can. The fact that in Smalltalk state is shared by default makes it hard, but yes, things like the futures, the promises, the things that, the structures that let you communicate safely, and, design those things as separate as you can. Avoid the evil of premature optimization. I've shown you some things I've had to do, but, if you're only doing things at 1,000 times a second, you don't need that. Do whatever is the clearest, makes the code easiest to read. I do have voluminous comments in my code about some of those things as to why there's like an empty block being sent ensure. Those wouldn't fit on the slide, but if you want to see the actual code, talk to me. Anyway, thanks for your attention. Questions?
Nice talk.
Thank you.
My question is, you said, well, don't use threads, right? I kind of agree, but now tell me, is there any Smalltalk in which I can avoid using threads? Because all of them kind of used it, right?
As far as I know, yes. That doesn't mean you have to actually use them unless you're in a position where you do need to use concurrency. And there are a number of situations where using concurrency is very beneficial. So, like I said, if you have to use them, use them. And if you don't, leave it to,
When you start Faro or any other Smalltalk, there are already threads running.
There are already threads running, in general. In GemStone Smalltalk, not so much, but yeah, but in ones with UIs, yes, typically. there are threads running.
Hi. My question is, on one of the first slides, you said that as long as we return the value which is somewhere between, somewhere in this time slot of execution, we are okay with it.
Yes.
But then, if I understand this logic, then the last two lines which you said are necessary, they're not really necessary, because you already found the value. Even if it was deleted, it was found in this time slot. So isn't it the...
Right. Yes, you are any value that was ever associated with that key. And that's the point, is that unless we check, let me see if I can find that slide. And I'm pretty much out of time, but let's see where that is. There we go.
Yes.
Okay. So the problem here is we find the key at this index.
Yes.
Right? We get suspended. That key is removed. A new key is added with a new value. We get that value. Now we have a value that belongs to a different key that at no point in time has ever belonged to the key we were looking for.
Okay.
That's an incorrect. That's an incorrect answer. So we have to check to make sure the key is still there.
But you saw that the key you have it as an argument, so it will never be garbage collected.
It will never be garbage collected. There are a few instances where there is explicit deletion.
And
That is not the predominant pattern, but there are a few instances where it is explicitly deleted.
one more question about GemStone.
Yes.
As I understood, the GemStone supports that you have multiple class dictionaries, right?
Yes.
So when you are saying that in a thread, we always pass all the global environment, is there any way that you pass there an empty class dictionary which has some primitives and then only does the work you want and
Right.
it can't access anything else?
The class dictionaries only apply when you're looking something up by name, which usually means either an explicit lookup by name or when you're compiling, the name of a variable will be resolved at compile time unless you do. So that becomes bound at compile time if it appears in a method. And then, of course, you can write methods that say, you can write explicitly, look up this name and send that message at runtime, and that would work. But yeah, the low-level execution machinery is not really set up for that kind of separation, although obviously there would be some advantage in doing so, although possibly also performance penalty.
Okay, thank you.
So, Georg has a question if we still have time. Do we have time? I think I'm out of time.
Quick question. Having the ensure block be guaranteed to complete sounds great, except if the ensure block causes an exception.
Yes, exactly what I said.
So is that caught?
Um,
Okay.
Okay, this is my Smalltalk philosophy hat now. I had to think about this a lot, and basically I think that an ensure block or if curtail block should always have the right to run to completion unless it signals an exception which is not caught. Right? Because it's conceivable that an ensure block would signal something that, like an error that would be caught and handled, and that would be okay. If you have better ideas, talk to me. I'm willing to discuss philosophy, and these things my ideas are not always the best in some of these areas that are a little less obvious.
Marty, I have another question. Here.
Yes. There you are.
Here.
I recognize the voice, but there's a lot of people out there and it's dark compared to here.
So I guess that we are talking about code that is not run on top of an optimizing compiler or something that would, for example, reorder code, right?
Well, I would assume that it would only reorder code when it knew that would not change the outcome.
Yeah, but if the compiler thinks that it's only running one thread, it might assume that is not changing anything and reorder
Yes.
it. And then
Yes.
that will be fatal.
Yes, if you have a compiler like that, hopefully that compiler has a way to tell it that this
Okay.
little piece of code must be not optimized in that way.
Do you, very short question. Do you see room for improvement semaphores? Did you ever talk to the VM because it's a VM thing?
Yeah, I haven't. I don't know. I don't know. You know, I would love to see improvement everywhere, but that one I don't know. Okay, thank you.